The next talk is by Darren Flynn, and he will present more computational applications of the Levi-Civita field. You may start.
Oh, okay. Thank you, everyone, for showing up. I know these are odd hours for some of you. And thank you for the invitation to speak. I really appreciate it. It's a privilege. So I'm going to begin with a review of the Levi-Civita field and some of its properties. I know Kodor and Angel both went over this a little bit, so I'll try to be brief. After that, I'll talk about the idea of a non-Archimedean delta function and some of the applications of that. And then I'll talk about specifically computational applications of the Levi-Civita field, and I'll describe some software I wrote along those lines. And then I'll conclude with some ideas for where things might go in the future and some, I think, interesting questions. All right, so the Levi-Civita field. So, of course, the support of a function is just the set of all points in its domain where it takes on non-zero values. And we call a subset of the rational numbers left finite if for any given rational number, the set of elements or the elements in that set less than or to the left of that rational number are finite. With that terminology, we can define the set R script, which is the set of all functions from the rationals to the reals with a left finite support. Now, I want to talk a little bit about notation here because the elements of our field are, of course, functions, but we're also going to be talking about functions defined on that field. So just to be clear, I'm going to use square brackets when talking about an element of the Levi-Civita field evaluated at a specific support point, and I'll use parentheses when I'm talking about a function defined on the Levi-Civita field. So with that notation, we can define addition and multiplication quite easily. Addition is defined pointwise. Multiplication is defined according to the second expression you see here. One thing to note is that because the support is guaranteed to be left finite, this is always going to be a finite sum. And so we never have to worry about problems of convergence or anything like that. This is well defined. We also have the function lambda of x, which, as we'll see, is basically the order of magnitude of an element of the Levi-Civita field. And we simply define that as the minimum support point of an element, or infinity if the element happens to be 0, in which case, of course, it has no support points. Okay, we can define the order on the Levi-Civita field. And the way it works is basically, we say an element is positive or greater than 0 if it takes on a positive value at its minimum support point. And similarly, it's negative or less than 0 if it takes on a negative value at its minimum support point. This is kind of the value it takes at any of the other support points is completely irrelevant. What we care about is the value at the minimum support point. We also have, I think this is actually the valuation here, but it's closely related to the ultrametric. And it's not going to play a big part in my talk today. I just want to point out that the topology induced by this order relation and the topology induced by the ultrametric are in fact equivalent. We call that the order topology or the strong topology. And I think Kodor already covered it when he talked about the student's dream. The series converges if and only if its terms are a null sequence. Okay, we can embed the real numbers into the Levi-Civita field using the embedding pi. Basically, if you take some number x and you want to figure out some real number x and you want to figure out what its equivalent on the Levi-Civita field is, its equivalent is the function which is 0 everywhere except for q equals 0, where it takes on the value x. So 2 would take on the value 2, 3 would take on 3, and so on. We also have the number d, which, as we'll see, I think on the next slide, is an infinitesimal number. This is defined as being 0 everywhere except at q equals 1, where it takes on the value 1. Okay, we say one element is infinitely larger than another if we can multiply the smaller element by any arbitrarily large natural number, and it will never be larger than the first element. Kind of a practical example here, we can now see how that d is infinitely smaller than 1. The key point here is if you take 1 and subtract n times d, no matter how large you make n, you will never change the fact that at the minimum support point, this expression takes on a positive value. And so 1 minus nd is greater than 0 for every natural number n. And that means that 1 is infinitely larger than d. In fact, you can do a similar thing and show that d inverse is infinitely larger than 1. Now, I told you about the strong topology, the order topology, and it's obviously very interesting, but it's not particularly convenient in terms of its convergence properties. For example, power series with real coefficients will only converge in the order topology in the infinitesimally small region about its center of expansion. So that's not very useful. In order to use kind of more normal functions that then have them converge on finite intervals, we introduce a weaker topology, which is defined in terms of this family of semi-norms. And basically the convergence criteria in this topology is that a sequence converges if each of the if the value of the sequence at each of its support points converges as a real sequence. So this is a weaker convergence criteria than in the order topology. It allows for more things to converge. In particular, it allows for power series to converge on a finitely large interval, on more than just an infinitely small neighborhood around a single point. So we have power series that we can work with, and from power series we can define analytic functions. These are just functions which are given locally by power series. One thing I'd like to point out is that each function has a rational number called an index, which is basically the same as the lambda function is for elements. The index of a function tells us something about the order of magnitude of a function. So if the index is equal to 0, then that's a finite function. Whereas if it were equal to -1, for example, that would be an infinitely large function. Okay, I don't want to get too bogged down in measure theory and integration, but I do want to convince you that we can do things rigorously. So on the Levi-Civita field, there is defined a Lebesgue-like theory of integration. And the reason it's Lebesgue-like is that it tries to emulate Lebesgue integration, but there are a few key differences. So for example, what I have on the screen now is the definition of the Lebesgue outer measure. This is what you'll find in a standard textbook. And unfortunately, we can't use this definition on the Levi-Civita field because this infimum is not guaranteed to exist. In the real case, it is. In the non-Archimedean case, it is not. Fortunately, we can come up with this slightly different definition of a measurable set. And it turns out that if a set is measurable according to this definition, in that case, the infimum from the previous slide will exist, and the two measures will agree with each other. So we're not doing things exactly the same as Lebesgue integration, but we're very similar. Okay, a few words about functions. I guess analytic functions are the bulk of what we work with. They're functions which are given locally by power series. A few key points. Well, okay, firstly, recall that D is an element of the Levi-Civita field. So to avoid confusion, we don't use the normal d dx to denote the differential operator. Instead, we'll just use capital Dx. What we can say is that every analytic function has a unique up to a constant analytic antiderivative. Now, the Levi-Civita field is weird, so a function may have more than one antiderivative, but only one of them will be analytic, up to a constant, of course. And then another key property is if we have an analytic function defined on an open interval, then we can always extend it to include the endpoints of that interval. That's key because we use that fact in the definition of an integral. Now, integration is also defined quite rigorously, and it's by design very similar to integration in the real case. We have all the useful theorems that you might want, and I won't go through and list them all for you, but there's one in particular that I'm going to need, and that is a version of Leibniz's rule that we have proven on the Levi-Civita field. And from Leibniz's rule, we get this proposition, which is the actual important one, which basically says if I have a piecewise analytic function in 2 dimensions, and I want to integrate along one dimension and differentiate along the other, I can interchange those 2 operations as long as the function I'm integrating is continuous. And that is going to play an important role in the next section, because now we're going to talk about a non-Archimedean delta function. All right, so first things first, why a non-Archimedean delta function? What's wrong with the real one? Well, the real kind of conventionally thought of direct delta function contains an internal contradiction. It's defined as being 0 everywhere, except at x equals 0, where it takes on an infinitely large value. But at the same time, it's defined so that integrating over it is equal to 1. And as an elementary result of calculus, if a function is different from 0 at only a single point, then its integral has to equal 0. So the delta function is not, in fact, a function. That's not to say that it can't be justified. It can be, but only using the notion of distributions, which is very different from the intuitive notion that, well, physicists like me like to use, which is an infinitely thin, infinitely tall spike. Now, on the Levi-Civita field, because we have infinitesimal and infinitely large elements, we can write out a literal function which has an infinitely thin, infinitely tall spike. And this is one way to do it here, the non-Archimedean delta function. It's not the only way to do it by any means. It just happens to be the kind of happy medium compromise that we settled on. Here's a little graph of it. Of course, it's being normalized so that if you integrate over any interval containing this infinitesimal interval from -d to d, then the result will be 1. And of course, if you integrate over any interval that does not contain that infinitesimal interval, the result will be 0. Now, we get the kind of quintessential delta function property is that if you integrate the delta function along with the second function, you will get the second function at a particular point. And that's not quite true for the non-Archimedean delta function, but it's close enough. The 2 expressions won't be equal, but their real parts will be equal. And since we're mostly interested in solving real problems anyway, that turns out to be good enough. Okay, a few other handy properties. The non-Archimedean delta function has a antiderivative, which you can see here. And when you restrict that antiderivative to the real numbers, it is identical to the Heaviside function. And one thing I'd like to point out is the fact that it's equal to 1/2 at x equals 0 is not artificial in any way. That emerged naturally just by insisting that the function be continuous. So that's kind of a pleasant surprise. Now, kind of the application that we looked at of the delta function was in solving differential equations. So before I get into that, I just want to give a brief review of the method of Green's functions in the real case. So for the next 2 slides, put aside the non-Archimedean stuff, and we'll just think about the real case. Suppose we have some linear differential operator, and we want to solve this differential equation where f is just some given source function. Well, one way we can do that is to first solve this second differential equation with basically the delta function as our source function. And the solution we get from that is called a Green's function. And if we ensure that the Green's function satisfies the same boundary conditions as we require our solution to, and then we integrate the Green's function along with our actual source function, then the result of that is the solution we're looking for. Yeah, this just here shows that if you satisfy the boundary conditions for the Green's function, then they'll be satisfied for the eventual solution as well. Okay, so it turns out that the non-Archimedean delta function can be used in the same way. So to give an example, let's look at Poisson's equation, one of the simplest differential equations. So we're given this differential equation, and we're given some initial conditions. And so the first thing we do is we try to solve for the Green's function. And this is actually a little bit easier in some cases in the non-Archimedean sense than in the classical sense, because we actually have a function to put in place of the source function. Whereas in the conventional sense, you have to do kind of some trickery with kind of having discontinuities in your solution and whatnot. So this is the general form of the Green's function for the Poisson equation. And now in the conventional sense, in order to have our solution have the correct boundary conditions, we need to have the Green's function have those same boundary conditions. And it turns out in the non-Archimedean case, we actually have a little more freedom than that. We don't need them to be exactly equal. We only need the boundary condition to be satisfied in its real part. So what that means practically is I don't have to define the Green's function at 0 as equal to 0. I can define it at r as equal to 0, where r is any infinitely small number. As it happens, choosing r equal to -d simplifies things considerably, and so that's what we do here. Now, it's worth noting here that this is where we're applying the theorem about being able to interchange the operation, the differential operator and the integrand. So we can do that if our integrand is continuous. So we require that the Green's function be continuous. But that only lets us get one differential operator under the integrand side. And the Poisson equation is a second order differential equation. So on top of having the Green's function be continuous, we also require that its derivative is continuous. That way we can move the second differential operator under the integrand side. And doing that, yields these results for our constants. These you get A3 and B3 from your initial conditions. You get A2 and B2 from making two pieces of the function continuous, and then you get A1 and B1 from making the other piece continuous with that. Now this looks pretty ugly, but if you restrict it, oh no, we haven't gotten to that slide yet. Okay. So now that we have a Green's function with the boundary conditions we want, we can simply integrate that along with any source function. I chose f of t equals t just for simplicity. We perform this integral, which is quite trivial, and we get this equation, the second from the bottom. Now, it has a real part and an infinitesimal part, and we only care about the real part. And when we take that, we get 1/6 t3, which is the classical solution to the Poissonic equation in this case. So it's nice that this works out. And of course, we've proven this more generally. I'm just showing you an example to illustrate. I want to show you one more example to illustrate something else. So here we have just the equation for a damp-driven harmonic oscillator. And we can follow the same procedure we did before. First, we solve for the Green's equation, which looks like this in its general form. And then using our initial conditions and using our requirement that the function be continuous and that its derivative be continuous, we can solve for the constants a1, a2, b1, b2, and so on. And they look like this. And this is ugly. And these ones are even worse. But if we take just the real parts, they just look like this. And so if we restrict our non-Archimedean Green's function to just the real numbers, we get something which is the same as the classical Green's function in this case. And so now we come to something which I think is really cool, which is we can actually do something that's not quite as easy in the classical case. Suppose you want to solve the differential equation for a damp-driven harmonic oscillator where your driving force is given by a sawtooth wave, a single sawtooth wave. Now, in the classical case, this is not so easy because it's not a continuous function. It can be done, but it requires some trickery. But in the non-Archimedean case, we can make a sawtooth wave that is continuous. And so we can just use the same method that we've been doing. We integrate it along with our Green's function that we found. We get some horribly long expression, but we take the real part, and that, again, in this case, conforms to the conventional solution. Now, obviously, this gets all very difficult with the algebra. You can see why we're interested in having a computer do all the work. I got these results using Mathematica. So that's kind of where we got to in terms of applications of the delta function. There's some more stuff we did. For example, it can be easily extended to higher dimensions, and we played around with using different coordinate systems. So we did some stuff in spherical coordinate systems, and it works there too. And yeah, I think that's just a really nice example of how we can use this field to produce a mathematical theory that conforms to our kind of intuition of the delta function. All right, moving on now to computational applications of the Levi-Civita field. I'll start by just restating some results that well, Kodo already covered, and they precede my own work. So I'm a little more pragmatic with my definition of a computer function. When I did this work, I did it all in C++. So for our intents and purposes, A computer function is just any compilable function made out of the standard math formulas provided in C++. And the idea here is basically there are some real functions that we know how to extend to the Levi-Civita field. Things like power series with real coefficients, the nth roots of things, negative powers of things. So we have this kind of small set of stuff that we know how to extend. And the question is, can we use that to extend even a greater variety of things? And it turns out we can. There's this result from Shamsuddin and Burrs, which shows that a real computer function in the previous sense can be expressed according to this, the first displayed equation. And that's important because on the right-hand side of that equation, we have only things that we already know how to extend to the Levi-Civita field. So we can just define the continuation of a computer function to the Levi-Civita field by first putting it into this form and then extending the bits according to how we already know how to extend them. Okay, so the theory is there. Oh, yes, okay, so why would we want to do that? Well, Kodo already talked about the fact that we can use this not only to calculate the derivatives of computer functions, but also to check whether or not they are differentiable at a given point. And from the perspective of someone who spends most of his time writing computer programs, that's super useful because computing derivatives is often one of the kind of hang-ups with programs, is that you can never compute the derivatives accurately enough for what you want to do with them. And this really seems to solve that problem. So now I'll talk a little bit about my implementation of these ideas. Now these aren't publicly available yet, but hopefully in the next couple of days, I'll have them up and running on GitHub once I've worked out a few technical kinks. So keep an eye out for that. And basically what I've done is I've defined a class. This is not a class in the mathematical sense, but in the computer science sense. It just tells the computer how to store an element of the Levi-Civita field up to any pre-specified depth. I've also defined the operators, the order relations, a few useful functions, and of course, all the trigonometric functions that you might want. So I'll just give you a few examples of how that works kind of at a computational level. So just to introduce some notation here for convenience, I'm going to use the subscript R to denote the real function. That is the thing that the computer already knows how to compute. The subscript LC is the continuation of the function, which is the thing we're trying to find. And then the subscript T is just a Taylor expansion of the function about some point. So for example, to compute the continuation of cosine, we take our argument, which will be a non-Archimedean argument, and we split it apart into its real part and an infinitesimal part. And then we apply the angle addition formula, and we can see that the real part alone we can just compute normally because it's a real argument. And the infinitesimal parts we can compute using Taylor series, and because the argument is infinitesimal, we can compute the Taylor series exactly up to any given depth that we happen to require. A similar thing happens for the natural logarithm. It doesn't have a convenient angle addition formula, but we can still find a way to break our argument into a real part and an infinitesimal part. We compute the real part using the real function and the infinitesimal part using the Taylor series. And again, we can do that accurately to any depth we want because the argument for the Taylor series is infinitely small. The most challenging part of this, for me anyway, was the inverse trigonometric functions. They don't seem to have any useful identities at all. but they do have a well-defined derivative. And it turns out we can pull the same trick using integration. So if we want to calculate the extension of arcsine, or the continuation of arcsine to the Levi-Civita field, we first express it as an integral. We break that integral into a finite part and an infinitesimal part. The finite part we compute conventionally, and the infinitesimal part, well, here we're integrating over an infinitely small interval, and so we can do that accurately up to any depth we want using Taylor series. And so in that's how we kind of computationally implement these functions. Yeah. So the first thing I did when I got this up and running was to verify the previous results regarding differentiation. So you can see here, this is the same function that Kodor showed you. And these are very similar looking results, but I want to be clear, these are computed with completely different software. I also compared against Mathematica and got very impressive results. So it's nice to know that works the way it's supposed to, and that verifies those results. One kind of aside here, we can use this. So as it happens, I was working with Bernoulli numbers, which I'll talk a little bit more about later. But what I noticed is Bernoulli numbers are usually defined in terms of a generating function, but they're never calculated that way. They're almost always calculated in terms of either the additive formula or a recursive formula. And that's because conventionally, it's not possible to find the derivatives of this generating function accurately enough to actually compute the Bernoulli numbers. But we can pull the same trick here that we did for derivatives, and excuse me, and we can actually find a closed form expression of sorts for the Bernoulli numbers. And in fact, we can do that in more than one way. You can do it with the generating function, but you can also do it with virtually any trigonometric identity that involves the Bernoulli numbers. I've chosen one involving the tangent here. And indeed, you can use these to accurately compute the Bernoulli numbers to a limited degree. There are other sources of error introduced here, which is why these aren't all in agreement. This is coming from rounding error, from the fact that that real numbers aren't stored to infinite depth in C++. You only have a limited number of digits to work with. But you can see that's particularly aggressive in, for example, the additive formula, but virtually non-existent in the tan formula. So it does look like there's some interesting potential here. Although this was only ever really kind of an interesting aside. The real kind of meat of what I wanted to do was look at integration. And the approach I took was to use Darbose Formula. Now this is quite a general formula for integration. Basically, the way it works is this integral of f of t is the thing that we want to find. The second line is a finite sum of things that we can compute. And then the bottom line is basically our error term. And kind of the idea here is that typically numerical integration works by evaluating the function to be integrated at many different points in the interval of integration, and then using some relatively limited approximation and then just trying to take the limit as you have as many points as possible. In our case, because we can compute derivatives so fastly or so quickly and so accurately, we can instead only compute the values of the function to be integrated at its endpoints, but we don't just compute its values, we also compute its derivatives to as deep an order as we can. And so I guess here we have a freedom of choice in terms of what we want our polynomial phi to be. If, for example, you chose phi to equal t to the power of n, then this would all reduce to a Taylor series. If you choose phi to be the Bernoulli polynomials, which is how I came to be investigating them in the first place, then this becomes the Euler-Maclaurin equation. And there are many different choices of polynomials you can make that, that produce related but slightly different approximations for an integral. And so I played around with a bunch of them and got some interesting results. If you're integrating just kind of polynomials of a relatively low degree, then this works really well. The central point Taylor series far outperformed anything else. And I compared this to things like Simpson's rule, as well as things like Mathematica's numerical methods. So for really simple integrals, this is quite effective. If you start working with analytic functions, the advantage sort of disappears. We still get a very high accuracy, and we still manage to beat symbolic computational methods, but Mathematica's numerical methods outperform ours. But there is one, I guess, kind of known weakness of Mathematica where we can definitely outperform it, and that is when it comes to high frequency functions. Now, when Mathematica gets a function that it's supposed to integrate, the first thing it does is evaluate that function at a bunch of points in the interval of integration. But if the sign changes, if the sign of the function changes very frequently, so frequently that it changes several times in between the points that Mathematica evaluates, then Mathematica will get an incorrect picture of what the function looks like. And so if you plug this function I have here into Mathematica with just default settings and just, you know, the most naive approach possible, then it will actually produce an incorrect result. Now, if you tweak the settings a little and try and kind of mitigate the issue, then you can get a more accurate result, but the time it takes to get that result increases dramatically. But because the non-Archimedean method doesn't just look at the value of the function to be integrated, but also looks at its derivatives, and its derivatives to a fairly deep order, it can understand quite easily that it's seeing a high frequency polynomial, and so it doesn't suffer from the same oversight. So there is some advantage to be obtained here, although admittedly the results aren't as clear as they are in the case of differentiation. Now that basically covers what I wanted to tell you about. There's, of course, never enough time in these research programs to answer all the questions you have. So I'm still left with some things I like to investigate if I ever get a chance. Firstly, is there any choice of phi in the Darbose formula which will make the error term infinitely small? If there is, then that would allow for kind of perfect integration. And then more generally, even if you disregard the Darbose formula stuff, is there any way at all to do perfect integration? Now, one of the most interesting things for me is that when you're computing derivatives in the way that we've done here, you're basically numerically computing the limit of a function. Now, you're computing the limit as x goes to 0, but I've always wondered if there's any way to go the other way and find the limit as x goes to infinity. Can I take a real function, extend it to the Levi-Civita field in such a way that I can plug in an infinitely large number and get out the limit as that function goes to infinity? I honestly don't know. I've tried a few things, but without much success. But if this is possible, it would be just incredibly useful from a programming perspective. And it would also probably answer the second question positively, because after all, integrals are defined in terms of a limit to infinity. And then finally, one thing I wanted to do, but kind of never, I was one bridge too far, as they say, is to see if I could combine the non-Archimedean delta function and all the kind of computational software for the purposes of solving differential equations. And I think that would be a really interesting thing to do. And I still hope to do that at some point, but it's not one of my priorities right now. And with that, I'd like to thank you for your attention. And are there any questions?
Thank you, Darren. Any questions?
Yes, I have one. I was wondering how you came about the formula for your non-Archimedean delta function.
Trial and error. We tried a bunch of different stuff. So one of the first things we tried, for example, was just a triangle. But in order to do that, we had to define it on 4 pieces instead of 3. And that just made all the equations just a little bit more difficult. So that's sort of the considerations we were having, but yeah, it was just trial and error.
Okay, so are there potentially other choices that might work, might have
absolutely, yes.
Okay.
Yeah.
Thank you.
Any other questions? Comments? Okay. In that case, thank you again, Darren. We'll take a break for about 15 minutes, and then we'll have the final talk for today. We'll see you back in 15 minutes.